So we know that if that diffuser has a really high velocity or really high velocity gradient when that jet is spinning apart, that it does break up flocks and breaks them so small that they come out the top of the plate settlers. So it is possible for the inlet diffuser to break up what would have been green flocks and make them red ones. That's bad. What's interesting though is it also all the time breaking up blue ones and turning them into green ones? Or not? There's more we have to learn there. What we do know is if the velocity gradient is too high in the jet coming off of that inlet diffuser, it does cause performance to deteriorate. Other questions? But apparently it doesn't turn blue flocks with lots of red particles inside them into clean blue flocks. Somehow it's not doing that transition for us, which would have been amazing. That would have been great. Okay, so here's the sedimentation tank. The water from the flocculator was entering right here. So this wall of the sedimentation tank lines up with the wall of the flocculator. So the flocculator then flows into this first channel, which is this channel where I have the arrow drawn here. And then in that channel, there are pipes that go down to the very bottom of the sedimentation tank system. And just to note that you can turn off one of these tanks, turn the water the whole way off, and then turn it back on again. And we at least have evidence of frequent success with doing that. So it means that even though the flocks settle out and form some sludge in the bottom of the tank, when you turn it back on again, that jet coming out of the inlet diffuser is enough to resuspend things. So another view close up of that jet showing water squirting out of, ooh, hang on. Well, okay, that's good enough. And you might wonder, like, why are we caring so much about this geometry? We ran into multiple problems with having sludge in the bottom of sedimentation tanks, and I'll show you some more of that later on. But one of the issues is that sludge goes anaerobic, and anaerobic means it produces methane, and that means that you've got little methane bubbles coming up through the water column in the tank. And I don't know if you can think about, like, if you turn this flock filter tank system into a soda bottle with little bubbles coming up through it, what those bubbles do is they grab a hold of flocks and carry flocks straight up to the top. So bubbles in one of these tanks is very, very bad. Actually, there's another treatment process called dissolved air flotation that uses that technique, but you have to decide which one are you going to use. Either you use dissolved air flotation and you collect the dirt off the top of your tank, or you use sedimentation and you collect the dirt off the bottom of your tank, and you don't want to try doing both of those at the same time. So our insight is that these tanks should have no settled sludge. There should be no sludge. It's just hanging out in the tank settled, because if it's settled, it'll go anaerobic. Whereas if it's in suspension, it won't go anaerobic, even if there is biological activity there, because there's enough oxygen in the water to keep it aerobic. And then I talked earlier about what happens if you slow it down. And this is an example of that. If we're using two different diameters of the tube that's injecting water into the bottom of this tiny little sedimentation tank, and we're keeping the flow rate the same. So that means that when we decrease the diameter of the tube, the velocity is higher. So if you look at on the left, there's a 3.9 millimeter diameter tube as the inlet. That has a high velocity. And on the right is an 8.9 millimeter, and it has a lower velocity. And as the jet gets bigger in diameter and is traveling slower, it becomes more vulnerable to the sludge actually coming in further and overtaking it and like burying the jet reverser. And so that's the idea that theta 2 is greater than theta 1. The sludge is actually coming in further onto that jet because that jet doesn't have as much momentum. So I'm going to go on to the flock hopper. So the flock hopper is where all the flocks come to that are excess flocks that are coming out of the flock filter, and they're accumulating in the flock hopper. And so the question is, well, how do we design the required size of the flock hopper? Because in our design thinking says that every dimension matters. And there's got to be something that determines how big this flock hopper has to be. And there's this notion that if you make it too small, it's going to fail somehow in this case. And if you make it too big, it's expensive. So we want to make it smaller. And the question is, what fails when you make it too small? The truth is, we don't have great equations for this yet, but we have at least some insight. But we have more to do as far as incorporating this into our design. This is a cool video to show at the very top of the flock hopper, sorry, very top of the flock filter, shows the flowing of the flocks over the top of the weir. That was too weird, wasn't it? Should we look at that again? I love the puzzled faces that I'm seeing. Do you believe this? Like, this is real. This video is in real time. It's not been sped up or slowed down. And it's showing what's right up here when this flock filter had grown up to be as tall as the weir. And you see this lovely thing of these flocks falling down, and it's like it's in slow motion. And it's like Niagara Falls. Like this is a fluid coming over the edge of a falls and it's falling down. But the reason that it falls so slowly is because the difference in density between the flocks plus water compared with water, that difference in density is very tiny. And it's the difference in density that determines how fast the flocks plus water are going to fall inside the water. If you want to convert that back to Niagara Falls, it's the difference in density between water and air that determines how fast the water over Niagara Falls falls down. If Niagara Falls was full of water below the falls, then there would be no falling over because the density of the incoming fluid and the density of the fluid that's there is zero. The difference is zero, and so there would be no velocity. Here, it's just a tiny difference in velocity. Flocks plus water are just a tiny bit more dense than water, and so it falls over like in slow motion. And that is happening right here inside the tank. This weir is what's setting the height that the flock filter grows to. So this is my idea of how we would need to design the flock hopper. First of all, we know that the weir controls how deep the flock filter is. The flock filter flow rate, the rate of flow out of the flock filter into the hopper. So it's the rate of that red stuff falling over the top of that hopper is a function of, this is based on mass conservation. It's based on the mass flux of particles into the sedimentation tank from from the flocculator. So almost all of the particles that come from the flocculator end up finally exiting the sedimentation tank or by falling over that weir. And because mass must be conserved, that's the concentration of clay or particles that have to be falling over that weir. So that's this notion that what's going in, the flow rate through your sedimentation tank times the concentration of flocks that are coming out of the flocculator must equal the flow rate into the hopper times the concentration of the flock filter, which is what's falling into the hopper. So that's just a statement of mass conservation. You can solve that for what the flow rate is over that weir. And that flow rate over the weir is usually small, although not always small. And then there's this other insight, and that is the velocity up through the flock filter in our systems is 1 millimeter per second, okay? And if we just suddenly turned the flow off to one of our sedimentation tanks, then the flow upward is 0 millimeters per second. And now the question is, how fast is the flock filter going to settle down? See the question? Normally, the flock filter is not settling down at all. The upflow velocity is 1 millimeter per second. If I turn that off, how fast does the flock filter drop? And the insight is, you just change your frame of reference. It's relative velocity in both cases. The relative velocity between the flocks and the water is always the same. So if you stop the water, the flocks are now going to drop at 1 millimeter per second. So if you suddenly turn off the flow, the flock filter is going to settle at 1 millimeter per second. And that means that the flocks that you send from the flock filter into the flock hopper are also settling at 1 millimeter per second. That's how fast they consolidate. And so that is the VZFF. That's the average velocity upward in the flock filter is 1 millimeter per second. And that velocity times the area of the flock hopper must equal the flow rate of flocks into the flock hopper. And so that gives us a way to calculate the area that we need for that flock hopper, the plan view area for the flock hopper. There it is. We haven't yet used this for the design of our tanks because there's been another constraint that set this dimension, but this is at least what the theory would lead us to. The problem is that we don't have good numbers yet on what the concentration of particles is in the flock filter.